So we're going to discuss elimination reactions. And as we talked about in class, elimination reactions are reactions that will end up yielding an alkene product. And the way that they yield an alkene product and why they're called an elimination reaction is because that alkene group is able to form due to the loss of a leaving group at an sp3 carbon and also the loss of a hydrogen from the carbon that is adjacent to there, the so-called beta position. So the elimination, the formation of the alkene occurs when during the reaction there is a loss of a proton from the carbon adjacent to the carbon that has the leaving group on. And the leaving group, remember, is typically a halogen. It's something that once it is broken away is going to be rather stable as an anion on the product side of the equation. We mentioned last time we met up in class primarily the E1 reaction mechanism. So the E1 reaction mechanism is one of the two routes that a reaction can follow to get to the elimination product, the alkene product. And as we were talking about E1 reactions, just to compare and contrast their features with the E2 mechanism that we're going to be focusing on today. In the E1 mechanism, remember that we're talking about the rate of the reaction. The rate of the reaction is proportional only to the concentration of the starting material that has the leaving group. It is not proportional at all to the concentration of the base. And so therefore we could write the rate equation as K times the concentration of RLV. And what this indicates to us is that the rate limiting step of the mechanism has to involve just the molecule that has the leaving group. It does not involve the base in any way, shape, or form. The base is not participating in that rate limiting step of our step-by-step mechanism. So that gives us a clue about what we need to think about in terms of the mechanism for this reaction. With the E1 reaction, another observation that has been made with that is the rate equation that we've seen here is most commonly observed in cases where the base being used is a relatively weak base. And some typical weak bases include such things as alcohols and water as examples. We're looking here typically for non-ionic bases, bases that have no formal charge, bases that are relatively stable, in other words, relatively weak bases. And the order of reactivity here for an E1 reaction is much like that of an SN1 reaction, where a tertiary carbon that's bonded to the leaving group is going to react fastest. Second fastest is going to be a secondary carbon that's bonded to the leaving group, and then primary carbons typically are not going to be able to be involved in the E1 mechanism. And with the E1 mechanism, we also commonly observe that if the reaction is going on at a secondary carbon, that there is carbocation rearrangements or 1-2 shifts taking place. So commonly, carbocation rearrangements or skeletal rearrangements are observed for reactions at secondary carbons. And the purpose of those carbocation rearrangements is to increase the stability of the carbocation intermediate. So looking at the E2 mechanism to compare and contrast this, what we're going to see with the E2 mechanism is that the rate of the E2 reaction is proportional to both the concentration of the molecule bonded to the leaving group and to the base that's present there. So we can write the rate equation as the rate is equal to K, the rate constant, times the concentration of the molecule that has a leaving group bonded to it, RLV, and the concentration of the base, which I'll just abbreviate as B with a lone pair of electrons. So B there is our base. And so we would say that this rate follows first order kinetics with respect to both the molecule bonded to the leaving group as well as the base. Typically with an E2 reaction, what we'll see is that rather than a weak base being involved in this mechanism, instead it's typically going to be a strong base. And when we talk about strong bases, we're typically talking about relatively unstable anions. So this would include such things as negatively charged nitrogen atoms. So for instance, sodium amide, NaNH2. If you were to look at that, there's an ionic bond between the sodium and the nitrogen. The nitrogen would have a -1 formal charge on that and would be quite unstable and therefore a relatively strong base. Sodium hydroxide and other species that have a negatively charged hydroxide anion are also suitable for this, as are a variety of other strong bases as well. The trick here is that it has to be a relatively strong base. For the E2 reaction, we're going to see here that the order of reactivity is similar as to the E1 reaction, where a molecule that has a tertiary carbon bond to the leaving group is going to be most reactive. Second most reactive is going to be the situation of a secondary carbon. Least reactive is going to be the situation of having a primary carbon bond to the leaving group. So the order of reactivity here is the same for E1 and E2, and the tertiary carbon is the most reactive. Where we see the difference between E1 and E2, looking at these different characteristics, is in terms of the rate equation. The rate of E2 depends on both the concentration of the molecule of the leaving group and the base. And also E2 is distinguished by the fact that typically we observe this particular reaction mechanism when we are working with a strong base, not a relatively weak base. So now we need to look at what the mechanism is for the E2 reaction. And we can also add here to our list, just to keep it consistent with the above information, that carbocation rearrangements are not commonly observed here. And for our purposes, we're going to assume that the carbocation rearrangements do not happen. It's a rare thing with the E2 reactions. So putting together a mechanism that accounts for these observations that we can make about the reaction, particularly looking at that rate equation up top here. Our rate equation suggests to us that the rate limiting step, the slowest step of the mechanism, we have to involve both the base and the molecule that's bonded to the leaving group. This scenario is analogous to that of the SN2 reaction, where in the SN2 reaction, we also saw that at the rate limiting step of the mechanism, the nucleophile and the electrophile, the molecule bonded to the leaving group, were both involved at that step. And we saw that the SN2 reaction was a one-step mechanism to go from reactant to product, where the nucleophile comes in and attacks the carbon at the exact same time that the leaving group is leaving. Similarly here for the E2, with this rather analogous rate equation, what's going to happen is that the base comes in and attacks a beta proton at the same time, the same moment that the leaving group is leaving. So just like an SN2 reaction, this is a one-step mechanism. So let's take a look at our reaction that can occur here. So we're going to do an example problem. So we'll take and start with this molecule. And we're going to react here with a relatively strong base. And so when we look at this particular reaction, and we're going to be asked to predict the elimination product. So when we say elimination, what should go off in your mind as you think about elimination reactions is you should always be thinking that what's going to happen here is we would expect to get an alkene as the product. So we need to go through how we're going to go about this. And when we were predicting the elimination product, that implies that we could be using an E1 or an E2 mechanism. To distinguish between these two, what we need to look at is primarily the strength of the base. So here we have an anionic base. And so that should lead us to predict that this is going to be an E2 mechanism, not an E1 mechanism. So again, we're looking at this, and if the base is a relatively strong anionic base, we're going to predict E2. If on the other hand, we'd used a weak base, such as water, we would be predicting that the elimination product would correspond to an E1 mechanism. The reason that this is of concern to us is the E1 and E2 mechanisms will sometimes lead to different products because of the fact that the E1 mechanism can involve carbocation rearrangements, while the E2 mechanism will typically not have carbocation rearrangements observed there. So we need to have some understanding of what mechanism is taking place here to enable us to predict the correct product in many cases. So we're predicting an E2 mechanism here. We said that the rate of this reaction is dependent upon both the concentration of the base and the concentration of the molecule that's bonded to the leaving group, implying that both of those species are involved at the rate limiting step. So we can piece this together analogously to the reaction that we did for the SN2 reaction, where the nucleophile came in and attacked at the same time the leaving group leaves. But here what's going to happen is that the base comes in and grabs the proton from the beta position at the same time the leaving group leaves. So we have to think about where our beta hydrogens are, and I'm going to go ahead and fill in those beta hydrogens on our starting structure in green, because these are the ones that are going to be prone to potential attack by the base. And we also have 3 of them over here as well. So we have 3 different types of beta hydrogens in this molecule, one that's associated with this 2-carbon chain, one that's associated with a 3-carbon chain, and one that's associated with that 1-carbon chain there. All of those hydrogens shown in green we would describe as the beta position, giving us that so-called beta elimination reaction. So then we'll go ahead and plug in our base here, which would be the hydroxide anion. We recognize that the oxygen has to be an anion because of the fact that it's bonded to a sodium. The sodium is much less electronegative than the oxygen, and so that's an ionic bond that we would anticipate being there. So what's going to happen is the lone pair electrons from the hydroxy group come in, grab a proton at the beta position, and at the same time that that happens, to avoid going really loud valence for the hydrogen, this pair of electrons connecting the carbon and the hydrogen has to come over to here. That's what's going to make our new alkene group. And then simultaneous to that, our leaving group leaves. So in one step, we're going to go from our starting material all the way to our final product. And this mechanism we've shown here is supported by the fact that we see that carbocation rearrangements are not typical, and we see that the rate is proportional to both the concentration of the base and the concentration of our starting material that has the leaving group bonded to it. So let's write out what the product would be resulting from this particular chemical reaction. So I'm going to go in and draw out our carbon skeleton here. And our new carbon-carbon double bond is going to be right here. So that's going to correspond to moving these electrons using that single double-headed arrow over from the carbon-hydrogen bond to make that new pi bond. And this isn't the only possible product, though. We could also make products that correspond to removing the beta hydrogens at the other 2 positions instead. So for those 2 options, what we would do is same mechanism. Only this time, what we're going to go after are the hydrogen atoms right here. And so we'll go ahead and bring in our oxygen atom from the base. So that's going to act as our basic atom there, and that's going to grab a proton from that beta position, forcing the carbon-hydrogen bond to break there, and the electrons from that are going to come over to make a carbon-carbon double bond at the same time that leaving group leaves. And then that is going to lead us to our product here. So going onward to our product and just mapping out what's going to happen here would give us this. And we would also, as the other product of each of these reactions, be creating water from protonating the hydroxide anion. And we'd also in each of these reactions be yielding a bromide anion as well. We're just focusing on the organic products of these reactions here. So that's a second possible product. And then continuing onward with this same process, we can go after the beta protons on our methyl group as another possibility to yield potential product here. Okay, so now we're going after one of the hydrogen atoms here on the methyl group. So I'm going to show one of those bonds explicitly. We're going to bring in again the hydroxide anion as our base, and we call this the base this time instead of the nucleophile because a base grabs a proton. A nucleophile is used to form a new bond to carbon. So the difference between hydroxide when it's acting as it is here and when it's acting as a nucleophile is just a matter of what's being attacked. So if the molecule is attacking a proton, that molecule that's doing the attacking is described as a base. If the molecule instead is using its lone pair electrons to attack a carbon, we refer to it as a nucleophile. That's the differentiation that we use here to distinguish between these. So electrons then, after that proton gets removed, as the proton's getting removed, the carbon-hydrogen bond breaks to make that new carbon-carbon double bond, and the bromine leaving group leaves, very analogously to what we saw in the mechanisms up just above. And then we can go ahead and draw out the product that would result from this. So for the product of this reaction, we're going to have our alkene group right here. So we have three possible constitutional isomer products resulting from this reaction. We need to ask ourselves, which of those products would be the most favorable? When we're thinking about which ones would be the most favorable, we're going to apply Zaitsev's rule, which we learned about last class period. And Zaitsev's rule tells us that the most alkyl substituted alkene product is the most stable and the most favorable, therefore, of the reaction product. So we're going to follow Zaitsev's rule to predict which of these products would be the major product or products. So we'll go ahead and also fill in here what we're indicating when we say Zaitsev's rule is, Zaitsev's rule says that the most substituted, specifically alkyl substituted alkene, is the most favorable, is going to be produced in the highest yield because of the fact that that's the more stable scenario. So if we look at these three products and we think about how many alkyl substituents are bonded to the alkene group, we would look at this lowest situation here and say that there's only two alkyl substituents because we look at how many alkyl groups are directly bonded to the alkene carbons, and we'd see an alkyl group here and an alkyl group here. Over on the left side, it's just CH2, so no alkyl groups there. So just two alkyl substituents. If we come up to the one here in the middle, we see there's three. 1, 2, 3, indicating with those green dots the three alkyl groups that come off of the alkene group. So this would have three alkyl substituents. And then we come to the very top and we see 1, 2, 3 alkyl substituents there as well. We said the most alkyl substituted is the most favorable. And so with that information in mind, what we can say then is that our major expected organic products are going to be these two right here. And both of those would certainly be produced in relatively high yields compared to the structure on bottom there, which we would expect to be a minor product of the reaction. So based on this information, that theoretically the reaction could yield multiple constitutional isomer products. Theoretically, it could yield 3 different constitutional isomer products. But in actuality, not all of those are equally favored, but instead there's a preference for a couple of them. What that indicates to us is that the reaction is what we would describe as regioselective. So we can say that this reaction is regioselective. And we could use this term regioselective to describe any E2 reaction, such as the one above, where there's multiple constitutional isomer products that could hypothetically be yielded by removing a beta proton. But in actuality, there's a preference for just one or a subset of those different possibilities. Not all of them are equally favorable. That's the term that we use to describe that as regioselective. So that's a good term to keep in your memory bank as a term that we need to assign to different types of reactions. When you're going through reactions, it's always a good idea to ask yourself, is this reaction regioselective? It is regioselective if hypothetically it could yield multiple constitutional isomers, but in actuality, it has a preference for certain constitutional isomers over others. That's going to be an indication to us that the reaction is regioselective. So just as is the case that E1 reactions compete with SN1 reactions for yielding elimination products, or alkenes, versus yielding substitution products, likewise, the E2 reaction is in competition with nucleophilic substitution as well. There are some things that we can do to drive an E2 reaction toward an elimination product rather than a substitution product. And one of those main things that we can do if we desire to drive a reaction toward an elimination outcome to yield an alkene, rather than toward making a substitution product, is we can use bulky, relatively strong bases. So bulky, relatively strong bases are going to favor the E2 mechanism over a nucleophilic substitution reaction. So bulky, strong bases are going to favor the E2 reaction over the SN2 reaction. So, for example, if we were to take a look at how to stage a reaction to give elimination rather than substitution, we would be much better off using as a base sodium tert butoxide. We have sodium bonded to an oxygen through an ionic bond there. And then that oxygen is connected to a tert butyl group. So if we were to look at the full or more complete structure of this, it would be a sodium cation in solution there, and in solution the anion would be a negatively charged oxygen bonded to a carbon, bonded to the 3 methyl groups. So those 3 methyl groups are going to create an awful lot of bulk around the molecule. And what that bulk is going to do is that's going to prevent a nucleophilic substitution reaction, because the oxygen there is going to be rather sterically hindered, and it's going to have a very hard time accessing a carbon atom in an SN2 mechanism. Because remember, the SN2 mechanism, that's the backside attack mechanism where the nucleophile has to come in and directly attack the carbon atom from the backside while the leaving group leaves. And so this bulky group here is going to inhibit SN2 from happening. So with SN2 being inhibited by having that relatively bulky group there that's basically sterically hindering the nucleophile from attacking the electrophilic carbon atom, what that's going to do is give the E2 mechanism instead a chance to prevail. And the beta position hydrogen is typically a lot less sterically hindered than the carbon atom that would be attacked in nucleophilic substitution. And so that beta hydrogen can relatively easily be accessed, even though there's this bulky group hanging off of the oxygen, the reactive location in the molecule. So this is going to be a much better choice if we want to do an E2 reaction over, say, instead using something like sodium methoxide. Even though the base strength of each of these two is relatively similar, the sodium methoxide, where we just have that O methyl group, is going to be much less sterically hindered. And so SN2 is going to be relatively more favorable than it would be if we were working with the than if we were working with the tert butoxide. So let's apply this toward an example. So what we'll do in this example is you're going to be asked to predict the major organic product, predict the single major organic product of this reaction. And so based on the features that are present here in the reaction, you're going to have to predict what the product would be of this. Okay, so we need to look at the Lewis structure of our base here to get a better idea about what is going on in this example problem. So we'd expect our sodium to be a cation, of course, and that's there just as what we call a spectator because it's not participating at any step of the mechanism. Instead, it's just along for the ride because the anion always has to have a counter ion associated with it. And then we'd have a nitrogen with 2 methyl groups bonded to it. And that nitrogen with 2 methyl groups bonded to it is going to be somewhat sterically hindered because of those 2 methyl groups. And that's going to help to favor the elimination reaction over a nucleophilic substitution reaction. So we'll bring in our lone pair electrons from the nitrogen atom acting as the base, and that's going to grab a proton from the beta position here. And so I'm going to go ahead and fill in my beta hydrogens. So we'd have a beta hydrogen here. We would also have 2 beta hydrogens over here as well. But what we're going to find is that if we attack this beta hydrogen, that would allow us to create a more substituted product than if we go after the other ones. And so this is going to be the Zaitsev's predicted product here. We take that carbon-hydrogen bond, move that over to make our alkene group at the same time that the leaving group bromine leaves. And that is going to give us in this one-step E2 mechanism our alkene group. And we're predicting here an elimination product because of the fact that putting in multiple methyl groups on that nitrogen is going to make that relatively bulky compared to if we just had sodium amide NH2. If we just had NH2, that's going to be quite a strong base, but it's going to be less bulky, and the less bulky, the less favorable the elimination reaction is going to be here. So the bulkier this is, the harder time it would have directly accessing the carbon that's bonded to the leaving group, and instead it's going to be more favorable to attack one of the hydrogens because the hydrogens are kind of hanging off the outside of the molecule, whereas the carbons are typically more buried in the inter, and so they're harder to reach. So it's an issue here of what type of attack can happen first. And if we have a strong base that's got some bulk associated with it, the attack at the beta position is going to happen faster than that nucleophile can reach the carbon to do an SN2 reaction. So this would give us our major organic product here expected of this reaction right here, again following Zaitsev's rule. Now we'll go ahead and do a few example problems of scenarios you might encounter for elimination reactions, for nucleophilic substitution reactions, etc. So we're going to try to apply some of the combined knowledge we've accumulated both SN1, SN2, E1, and E2 reactions. So we're going to start with an example here where you're going to be asked to provide the substitution product for this particular reaction. And it's always a good clue to look for when you're taking a look at a reaction, trying to predict what's going on there. Sometimes there'll be even a clue like to predict the substitution product of a particular reaction. When we say substitution product, What that means is the nucleophile is going to be attacking the electrophilic carbon at some point during the reaction. So you're going to end up substituting one atom or group for another during the reaction. You are not going to be creating an alkene. So one of the keys to getting this problem is to keep in mind that you have a big hint here when we say that it's a substitution reaction. So let's go ahead and take a look at the exact example that we'll be doing here. So we have a secondary carbon reacting. It's reacting with a relatively weak nucleophile and a weak base. And when the nucleophile is relatively weak, meaning non-anionic, that's typically going to enable the leaving group to leave before the nucleophile attacks because of the fact that the nucleophile is not particularly strong, not particularly reactive. So we're going to say that this is going to be an SN1 reaction. So what's going to happen in this SN1 reaction, since we said we have to be going for a substitution product that leaves us only with SN1 and SN2 as possibilities, is the leaving group breaks away, and that's going to give us our carbocation intermediate. This accounts for why the rate limiting step, the slowest step of the mechanism, is first order, depending only on the concentration of the electrophilic molecule, the molecule that has the leaving group bonded to it, is because this is the slow step of the mechanism. The rate limiting step is the leaving group breaking away to give this relatively unstable carbocation intermediate. So that's our first thing that happens. And then second thing that happens as we're going toward predicting the product is that we can have a 1-2 shift take place if it will stabilize that secondary carbocation to make a tertiary carbocation. So secondary carbocation can be stabilized by moving this hydrogen over in that 1-2 shift. The electrons from the carbon-hydrogen bond are going to come over, attack that positively charged carbon, and that's going to give us movement of that hydrogen atom, or what we call a 1-2 shift, so that now that hydrogen atom is on this carbon. And there was already one hydrogen atom there to start with, and so therefore that carbon atom that has that new green hydrogen now has a complete octet. What's now missing the octet is this carbon atom right here. So now we've made a tertiary carbocation out of a secondary, definitely a favorable thing to do. And then from there, we're really only asked to provide the product of the reaction, not a full mechanism. So we don't really have to go through every step from here on out. We just need to know typically what the carbocation is that's going to be the major carbocation going through this process, so that we can get to accurately predict the product of the reaction. So from here, I'm not going to continue to show every last step of the mechanism, so that's not really what we're asked to do. We're asked to provide the product of the reaction. So now that we've rearranged the carbocation, all we need to do is remember from our previous mechanisms that we draw onto the nucleophile has to bond here. And so our nucleophilic atom is going to be the oxygen atom because that's what has those lone pair electrons. And during that mechanism, the O methyl group is going to become bonded to that carbocation, and that proton there from the OH group is what gets lost during the final deprotonation step of the mechanism. So going ahead and writing out the final product here that corresponds to that carbocation that we had as our intermediate, we need to put our nucleophile right here. And that's going to be our oxygen bonded to the methyl group, our OCH3 group, because the oxygen is going to come in, form a covalent bond to the carbocation to lead us here to our final substitution product. And we have no chiral centers or anything to consider here in this final product. This is an achiral molecule. So that's going to be our substitution product of this reaction. Remember, though, that the SN1 reaction, the substitution reaction, typically competes with an elimination reaction. So that's one reason why I gave you this clue here that this was a substitution reaction, because otherwise, without that knowledge in hand, it would be really difficult to predict what the major product of the reaction would be, because typically substitution reactions and elimination reactions are going to be in pretty direct competition with one another if we're looking at a relatively weak base being involved here, such as the alcohol. So now what we can go in and do is be asked to provide the elimination product of the reaction. So in the real world, what would typically happen would be that we would end up with a mixture of the substitution and elimination products. Generally, I'm going to ask you for one or the other, or possibly both, but there should be some clues here to indicate whether you need to go after the alkene product, the key word there being elimination, or whether you need to go after the substitution product. Of course, the key word in the problem would be substitution. So let's go ahead then, and we'll start with the same reactants. And now you're asked to provide the elimination product. So for the elimination reaction, much like the substitution reaction, we're going to assume this is an E1 mechanism because of the fact that it's a non-anionic weak base. If we're a strong base, we would expect that the E2 mechanism would dominate instead of the E1. In the E1 mechanism, remember that means the rate limiting step is unimolecular and involves just the molecules of the leaving groups. That rate limiting step is the same as the rate limiting step for our SN1 reaction, where the leaving group leaves to give a carbocation. That's going to leave us right here like this. And just as in the problem above, we'd have that carbocation rearrangement using the same mechanism that we saw above even to give us our carbocation intermediate right here. And then what I'm going to go ahead and do is relative to that carbocation, I'm going to fill in the hydrogens that are beta to that, because those are the hydrogens that are going to be subject to being removed during the next step of the reaction, the elimination step. And you'll notice that these hydrogens that I've shown in green are totally symmetrically substituted around the carbocation, so it doesn't matter which of those we go for, we're going to end up getting the same product one way or the other. So then we take our base here, and we refer to this as a base because it's going to be grabbing a proton there. And once that proton has been grabbed, at that same moment, the electrons from that carbon-hydrogen bond have to come over to make our alkene group. And then at that same moment, we will end up getting our product out of this. So our final product corresponds to moving in that carbon-carbon double bond right there, and that's going to make our final alkene product. We refer to this as the substitution product. The elimination product. Elimination product, always going to have an alkene group. Substitution product, like we've shown just above there, is always going to have just substituted one group for another. All right, so we'll do one more example before we wrap up our discussion of elimination. Much like with the previous examples, we're going to be asked to predict the major organic product of this reaction. We're going to predict the major product. And what we're going to start with here is 2-bromo 3-methyl pentane. And we're going to go ahead and react that with the following molecule. And we're going to ask what the final product would be of this reaction. So we're not given any additional information here about whether to expect this to be an SN1, SN2, E1, or E2 reaction. So we're going to have to make a conclusion about what's most likely to happen here based on the reactants that are present. So let's go ahead to get this started and go ahead and draw out the structure of our 2-bromo 3-methyl pentane. So we need our 5-carbon chain in there, of course. At position 2, we'll put a bromine atom. Position 3, we'll put our methyl group. And then from there, we have our base. And we need to recognize here that in this, there's an ionic bond between the potassium and the oxygen. And it's going to be the oxygen that carries that negative formal charge to make that oxygen quite strongly basic. And then we have that cyclohexyl group tagging along with it. And what we should think about here is the fact that this cyclohexyl group is relatively bulky. If we were to build a molecular model of this, that's going to adopt that chair conformation, and it's going to be pretty bulky. So what we've talked about previously is that when we're thinking about what the preferred product is of a reaction, if we have a bulky basic group, those are going to tend to favor elimination reaction over substitution reactions, particularly since this is basic, it's going to favor the E2 mechanism, because remember that when we were talking about E1 versus E2 and distinguishing between the two back at the beginning of this discussion, we said that if the reactant is a weak base, it's typically going to favor E1. If it's a strong base, it's going to favor E2. Anionic bases are generally strong. So this is an oxygen that has a negative formal charge, so we can predict that's going to be a relatively strong base. So let's go ahead and go about the E2 route for this. Because of the fact that we have a pretty sterically hindered base, that is relatively strong. Strong sterically hindered bases are going to favor E2. So we'll have our oxygen atom come in, and that's going to attack a beta position proton following Zaitsev's rule. So we have a couple of different beta position protons that we can go after here. I've highlighted those in red. And the one that we're actually going to favor attacking is going to be the one on the right here, because that's going to give the Zaitsev predicted product, the most substituted alkene product. So we have the oxygen come in, attack that proton. That's going to force the oxygen-hydrogen bond to break. The carbon-hydrogen bond to break, and the electrons from that bond to come over to make a new carbon-carbon bond. At the same time that that happens, the leaving group has to break away. So we'll do that like so. And then we'll go ahead and draw out our product that would result from this particular reaction. So we get our carbon-carbon double bond in right there, and that's going to give us our molecule that's substituted with 3 alkyl groups, making that more preferable by Zaitsev's rule than putting the carbon-carbon double bond at the alternative location between the carbon with the leaving group and the one with the methyl group there toward the left-hand side of the molecule. So this would be expected as our major organic product. And we expect to make much more of this elimination product than we do the substitution product, because of the fact that when we look at the structure of the base, we see that it is pretty bulky and it's quite strongly basic. If it were a weak base or it were not as bulky, we would expect that substitution would become more favorable then. And there's definitely a gradient here between favoring substitution, favoring elimination products. It's rare that you have a reaction that would yield exclusively one or exclusively the other. Instead, we're really looking for what tilts the equation toward favoring elimination over substitution or vice versa. And certainly having a bulky basic group is going to tilt the equation toward favoring elimination rather than substitution. So this pretty much wraps up our discussion of elimination reactions.